All right, so set of notes in Schoology. Again, take your own or use the ones I provided. This is chemical reaction equations, molar and molar mass is the topic of this set of notes. All right, so we did discuss the law of conservation of mass the other day. Here's a quote from the scientist who is credited with it, Lavoisier. We may lay it down that as an incontestable axiom that in all the operations of art and nature, nothing is created. An equal amount of matter exists before and after the experiment. Upon this principle, the whole art of performing chemical experiments depends. And indeed, this work led us to the explosion of understanding chemistry in the 1800s and directly led to the development of chemical equations. Okay, so chemical equations are just representations of chemical reactions. In a chemical reaction equation, we have very distinct separate parts. First of all, we have the reactants. Those are the things that appear on the left side of the equation, or in other words, they are the chemicals that we have before the reaction. We have products that appear on the right-hand side of the equation, or the chemicals that appear after the chemical change has occurred. Next thing in a chemical reaction equation are the state symbols, okay? So the states of the reactants and products are written in parentheses to the right of each compound. Again, gases are G, solids are S, liquids are L, and if something is dissolved in water, we put AQ for aqueous. And last but not least, we put in coefficients to balance the equation. So we put a 2 there and a 2 there. This is where we come back to Lavoisier's statement. The purpose of balancing an equation is to show that no matter is created or destroyed. Okay, so if we just look, before the reaction we have 1 carbon, 4 hydrogens, and 4 oxygens. After the reaction we have 1 carbon, 4 hydrogens, and 4 oxygens. Without those coefficients there, that's not true. It looks like matter is created or destroyed, and so as a result of that, we can't have it. We need to balance. Okay. At this point, it is important for us to stop and note the different numbers that we find in chemical equations. Okay. We have coefficients, which we put out in front. We have subscripts, which we put down below. And again, just to remind us that the subscripts tell us the number of atoms of each element in a molecule or a formula unit. The coefficients tell us the number of molecules or the number of formula units involved. So lots of different ways to balance an equation. And so you learned this either over the summer or last year. So we're just going to have you give a try of balancing this equation that's here on this page. When you're done doing this on the left side, come on back and we'll do it together. All right, when I do balancing equations, I typically use a right to left systematic method, which I just keep going left to right, left to right, left to right on one side of the equation until I get everything balanced. Okay, so start with 1 sulfur, I'm good. 1 hydrogen, 4 hydrogens, so I'm going to put a 4 out in front. 4 nitrogens, 4 nitrogens. 12 oxygens, and over here I have 4, 8, and 1 oxygen, so that's 13 altogether. At this point I'm going to employ what I call even-odd strategy. This number is odd, so I find what is odd and I double that. And then I go back to the beginning and I start over. So now we're going to go ahead and we still have 1 sulfur, 4 hydrogens, but over here now I have 2 plus 4, so 6 hydrogens. So I'm going to go ahead and change this to a 6. 6 nitrogens, so I got to change this to a 6 on this side, and that gives me 18 oxygens altogether. So this is 4 plus 12 plus 2 is 18 oxygens, and we've been balanced. That simple back and forth method works well for most equations, but there are some equations that are really hard to balance. We won't see any of these on a test in this class. Most of ours will be straightforward. But if you ever run into a very hard equation to balance, there is a method that works on any equation. And so I've put a reference sheet in Schoology called Tool for Balancing Hard Equations, that if someday you're down the line in a college chemistry course and you go, hey, this is really hard. How can I balance this? You can use the tool for balancing hard equations. All right, so that's equation basics. So the next thing that we do with equations after we write them out is we'd want to translate them into a scale that works for humans. And so the first portion of that is for us to talk about compound weights. All right. First kind of compound weight is a formula weight. Okay, so a formula weight is simply the sum of the atomic weights for the atoms in a chemical formula. So I go ahead and I go to my periodic table for CaCl2. I have 1 calcium in there. They each have a mass of 40.08 AMUs on the periodic table. Chlorine, I have 2 of them. They have a mass of 35.453. I do the multiplication, I do the addition, I apply sig-fig rules, and I get 110.99 AMU. That is the formula weight for calcium chloride. Formula weights are for ionic compounds. Likewise, molecular weights, which are for covalent or molecular compounds, is the sum of the weights of an atom in a molecule. So for example, if we have ethane, C2H6, we would again take 2 times the mass of carbon, 6 times the mass of hydrogen, do the multiplication and add them up and then apply sig-fig rules, and we would get 30.070 AMU in this particular case. So then an extension off of the formula weights is something called percent composition. So we can find the percentage of the mass of a compound that comes from each of the elements in the compound by using this equation. So the percent that is a particular element is equal to the number of atoms times the atomic weight divided by the formula weight of the compound. Okay? So in other words, the formula weight of the element in question times divided by the formula weight of the compound times 100 because it is a percentage. So for example, the percentage of carbon in ethane, right? Ethane we had a couple slides ago, it's C2H6. So the mass of carbon is, there's 2 of them, so 2 carbons times 12.011 AMU divided by the mass of the whole thing, 30.07 AMU, times 100, and you get 77.887% carbon. That obviously means that the rest of it is hydrogen, so you can either calculate that out or you could just go 100 minus that answer that's over there. All right, so those are things when we're dealing with things on an atomic level. But what happens if we want to deal with things on a human level? Well, then we have to bring in the concept of the mole and molar mass. Okay. So in chemistry, we have defined something called Avogadro's number as having 6.02 times 10 to the 23rd of anything. So if I have 1 molecule of water, that's great. If I have a mole of water, I have 6.02 times 10 to the 23rd molecules of water. Okay. By definition, a mole of carbon-12 has a mass of 12.00 grams, and so from there, you can go and you can connect the number of particles to the mass. So by definition, the molar mass is the mass of 1 mole of a substance, 6.02 times 10 to the 23rd particles of that substance. It usually is expressed in terms of grams per mole. The nice thing about molar mass is the molar mass of an element is simply the mass number that we find on the periodic table with the units grams per mole instead of AMUs. So AMUs for individual molecules or formulas, grams per mole for moles of things, for molar mass. And so we can use moles then. We can use that molar mass to change from grams of a substance to moles of a substance, or from moles of a substance to grams of a substance. We can use Avogadro's number to go to the number of formula units or number of atoms from moles as well. So essentially what moles do is they provide a bridge from the molecular scale to the real world scale, from us talking about formula units of things to us talking about grams of things. All right, so now that we've got chemical formulas, now that we've got chemical equations, and we've got molar masses, we can go ahead and we can use this to find empirical formulas for things. The other day we talked about formulas. One type of formula is the empirical formula. It is the least whole number ratio of chemicals involved in making a substance. And we can actually find the empirical formulas using experimental evidence. All right? So we can calculate the empirical formula of something from the percent composition or from lab masses. Okay? If we have the percent composition, we just assume we have a 100 gram sample, and then we can turn grams to moles and then calculate a mole ratio for each of our chemicals. How do they compare to each other? This is going to be the focus of our POGL on Friday. In the lab, a way that we can often deal with this is especially if we've got organic compounds that are primarily made of carbon, hydrogen, and oxygen, they are routinely analyzed through a process called combustion analysis, where we basically burn them, and then because it's a combustion reaction, we're going to get carbon dioxide and water out of it. And so as a result of that, you can get the amount of carbon in the compound based on how much carbon dioxide is produced, the amount of hydrogen based on how much water is produced, and the oxygen determined by the difference using law of conservation of matter. This is going to be the focus of our POGL on Monday.